All right. So today, I'm going to be introducing graphs to you. Now, you're all familiar with making graphs. You're all familiar with analyzing graphs, right? But hopefully this helps to make graphs seem more useful and more purposeful, because there's a lot of times in science and math where it's just like, we're graphing because we're told we need to graph. In this case, we're going to try and make it seem like we're graphing because there's purpose behind it and it's useful. So, to start off, I'm going to show you these two graphs here. And what if I told you that this graph, with the line that goes up, is the same exact information as this graph that has a line that goes across? So normally if you'd heard that, you'd say, oh, that doesn't make sense. But hopefully by now you're learning that in physics, things that used to not make so much sense or used to not be so clear become clear. So let's take a look at this, all right? So to start, I'm going to show you this basic graph, right? So we have a data table, and from the data table, we put it onto the actual graph. Here's rule number 1. When you watch a YouTube video, where is the time scroller? So, on a YouTube video, let's say this was a YouTube video, you would adjust the time with a line like this, right? Like if you want to go back, you grab it and you click it back there, or if you want to go forward, you click it there. But the point is that anytime we have a graph that includes time, time goes on the x-axis, just like how time is on the x-axis of a YouTube video, just like in this, like down here, right? So that's the time down there. All right, that's pretty cool. That's pretty cool. So, if we were to graph this, this is what this would look like. So the distance is going up by 2s, an interval of 2. Time is going up by an interval of 1. So after 1 minute, the distance should be 2. So after 1 minute, the distance is 2. So we would put a dot there. After 2 minutes, the distance is 4. So we put a dot there, and blah, blah, blah. We connect a dot with a line like we've always done ever since, I don't even know, elementary school? How long have you been making graphs? I don't know. All right. So this is going to be showing us distance versus time. So, let's just see what the velocity formula can tell us about this. So, v equals distance over time. So if this is a graph that's about distance and time, we could literally name this velocity. We know that this is a velocity graph because it is showing us a distance and a time. All right? So, if we know this is a velocity graph, what is the velocity of the object represented in this graph here? Well, let's try it out. So we're going to have multiple different times, and we're going to see if the velocity changes or if the velocity is constant. So, at time 1, v equals d over t. The time at time 1, obviously, t equals 1. We don't even have units for this because it's just an example. D equals, so time is 1, distance equals 2. So for the velocity formula, we have distance over time, 2 over 1 equals 2. Let's try 5 out. The time for 5, of course, is 5, right? The distance is going to be 10. So if we plug that into the formula, a distance of 10 divided by a time of 5, that equals 2 again. So we're finding a nice consistent. Let's just make sure that it's true for the whole thing. Time 9. So we have a time of 9 and a distance of 18. We know that 18 divided by 9 equals 2. So this is a constant velocity of 2, okay? So we have a constant velocity of 2. So if we were to graph this where we have time on the bottom, and the velocity is going to be a velocity of 2 throughout the entire time, that means this graph will look like this, okay? So in this case, we have a velocity and we have a time here, right? So if we have a velocity and a time here, if we look at the velocity formula, v equals d over t, we're given velocity and we're given a time. So that means we can solve for distance using this. So if I get rid of time on one side and move it to the other side, now I have t multiplied by v equals d. Or time multiplied by velocity equals your distance. So, do these show the same information? These two graphs. Do these two graphs show the same information? In a way, they do, right? Because using a distance and a time, we can solve for velocity. So solving for velocity on this graph with the distance and a time, v equals distance over time. So we can use the information from this graph, let's say this point here. If we wanted to know the distance an object travels after 5 seconds, so we have time equals 5 and distance equals time is 5, so the distance is going to be 10. So that means that the velocity is going to be 2. All right? Now in this case, if we go at a time of 5, right? And what do we have here? So t equals 5 on this graph. What is with the 5? Oh, velocity v equals 2. And we need to solve v equals d over t. What don't we have? We don't have a distance. So if we set distance to be alone, we cancel out the t. We end up with t multiplied by v equals d. So if I do t multiplied by v, 5 times 2, or 5 times 2, equals a velocity, a distance of 10. And this graph had a distance of 10 when the time was 5. And this graph had a distance of 10 when the time was 5. Okay? Hopefully this isn't too confusing, right? So, yeah, hopefully it wasn't. So, what would be happening to the velocity of an object if we have a graph that looks like this? So again, first we need to look at the axes. We are given a velocity and we are given a time here, right? So we're given a velocity and we're given a time. On the last one, we had, so I'll bring it back. This last one where we had a velocity and a time, this was a constant velocity, where it was always 2 meters per second was the velocity. In this one, our velocity is changing. At time 0, there is no velocity, but then as we go higher in time, so time goes from 2 to 4 to 6 to 8, the velocity jumps as well. It gets higher and higher and higher. So what's happening to this object? It's starting slow, and then it's going faster and faster and faster and faster and faster and faster. We call that an acceleration. An acceleration is when something speeds up or when something slows down. So the definition of acceleration is a change in velocity. And in physics, when we write change, we don't use the word change, we use a triangle, a delta. So change in velocity divided by a change in time, that's what acceleration is. Acceleration is a change in velocity over a change in time. So let's take a crack at that, okay? So, we have a change of velocity over a change in time. So this is another way of writing the formula, just rearranged. Don't worry about that yet. What is the acceleration of an object between time 2 and 6 on this graph? So let's try it out. So we're given the change in time. So let's just write this out. Don't worry about this formula yet. We will get to it, but don't worry about it. Acceleration equals change, triangle, change in velocity divided by a change in time. All right? So a nice thing about a graph is that it gives you this stuff. You just have to find it. So at time 2 and time 6, okay? So we can set this up. We know our change in time. I always like the big number first. So this is in seconds. 6 seconds minus 2 seconds, because that's what they give us. 6 seconds and 2 seconds. And now we have to find the velocity at these different locations. So in this case, the velocity initial is going to be 2 meters per second. While at minute 6, the velocity final is going to be 6 meters per second. Okay? So in this case, our change in velocity is from 6 to 2. 6 meters per second minus 2 meters per second. Okay? So what's the acceleration of this object? 6 minus 2 is 4 meters per second. Divided by 6 minus 2 is 4 seconds. 4 divided by 4 is 1 meter per second squared. The squared only happens because we're dividing a divided second. So meters divided by seconds, that's actually going to square our seconds. 1 meter per second squared. All right. Probably a lot of information, but what does this mean? What this means is that every second that goes by, I said second once, the object is then moving 1 meter per second faster. I said seconds twice now. So listen to that again. Every second that goes by, so as the clock ticks, every second that goes by, this object is going to be moving 1 meter per second faster. So that's where the squared comes from if you just followed my English. All right, so what this is showing us that after 1 second, so between 0 and 2 seconds, the object is going 1 meter per second. After 2, it's going even faster, 2 meters per second. After 3 seconds, the object is going even faster, 3 meters per second, and so on. So the object keeps going faster and faster and faster. And that's why we end up with the units meters per second, or meters per second squared. Okay? So, in this case, that last graph shows us a velocity that's steadily increasing. So that means the acceleration is going to be increasing by 1, which is why the acceleration here is 1, because it's going faster and faster and faster and faster. Every second that goes by, we add another meter per second. Hopefully that makes sense. If it doesn't, then at least the graphing should make sense. And as you work through the graphing and work with more formulas, hopefully it falls into place.